Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. Today we will start the topic of drying. Drying, we know that it is very important unit operation and most commonly practiced unit operation in food processing section. Since a long time we are practicing drying on many varieties of the product, mostly the grains, fruits and vegetables, and sometime sometime for preparation of the baby food. Okay, then different kind of fruit pulp powders and all, we are using different kind of drying techniques. So drying is basically removal of moisture by evaporation from solid or liquid material to a very low moisture level. Okay. So there are many dried products available in the market, and that is a mostly practiced method for food processing. So why we do this bulk removal of the moisture from the product, and we have also we have learned evaporation, there also we do the removal of the moisture, but the difference is the end product in the evaporation is mostly a concentrated liquid, but the end product in the drying is a solid, okay, or mostly a solid or very low moisture content porous structure if we deal with the fruits and vegetable. Okay. So in this case the objective of the drying is first is to preserve the content, okay, to preserve the food for a longer duration of time. Now what are the main reasons that can spoil the food? Firstly, if you think about the microbial contamination, so we have read the microbial kinetics in this particular course. So for the activity of the microbes, they need a certain moisture level. Okay, high moisture level is required for activity of the microorganism. Beyond a certain amount of moisture content, for let us say water activity 0.8 or above that, chances of the contamination of microbe is higher, but if you reduce the moisture content of the product to a safe moisture level, so the microbial contamination will be reduced. Okay. So the first function of drying is to reduce the moisture content or thereby reducing the water activity, so that it can be preserved for a longer duration of time. Okay. Now lowering of water activity not only reduce the chances of microbial contamination, but also reduces the chances of enzymatic activity, because enzymes also need a certain moisture content for their activity, right. So the first thing is preservation as a result of depression of water activity. So lowering of water activity is a very important phenomena in terms of storage point of view for any food material, right. And mostly if you see the fruits and vegetable, they are having very high moisture content, around 80% or 90% weight basis moisture content they are having. So reduction of water activity is the first and important step of drying method. Second is, what happened that since most of the food products are having very high moisture content and we are evaporating that moisture, so obviously the volume is reduced, okay, weight also is reduced. Now because of that, what will happen, the handling will become very easy. Okay. So transformation of a food to a form is more convenient to store it, pack it and transport for different use. That become easier if you perform the drying. Okay. And convenient for form in the sense like we have converted the bulk milk to the milk powder. So how much the volume reduction may happen, you can think about. Okay. So this is very effective method for storing as well. Then imparting to a food product a particular desirable feature. What happened that because of drying, some flavor development and the color, desired color is also it also comes on the product, but we need to look carefully that there is a thin line between the off flavor development or there is a color development. So, we need to keep the eye open, so that whenever we perform this drying we should optimize those process based on the requirement of the product. Optimize in the sense the factors we need to control during the drying operation. For example, we will come to that eventually, that how we perform different drying method. So, the main thing is the temperature we need to control, okay. Then the moisture level, the safe moisture level to which we need to store it, that we need to optimize, okay. So, that all the required quality changes can be done, but no undesirable changes or contamination can come to the product surface. Now, the most important aspects of drying mechanism is to know the kinetics of drying, okay. This is very important because there are many factors that can cause changes in the kinetics of drying, okay. So, whether it follows a constant pattern or it will deviate, okay, in what rate drying has happened, and that that has effect to the product in the long run, okay. Because by drying, not only the moisture removal is our aim, but we also want to keep the product quality intact, okay. And mostly these food products are very high heat sensitive, and they contain many thermolabile nutrients, vitamins, okay. So, those antioxidants, okay. So, those may get damaged if they exposed to very high temperature or so. That is why sometime it may happen that some product in the initial stage, when moisture is high, require a different temperature zone or temperature level, and when the moisture has been reduced, then a different temperature or even altogether a different mechanism you may use. For example, in a high moisture product, if initially you can go for the convective drying method or solar drying method, and in the latter stage when the moisture is very less, and that also in the pore space of the inner layer of the food material, then you can try vacuum drying, those kind of method where the drying rate will also be faster and the product quality will be intact, right. So, quality is important, kinetics is important, and the third thing and the very important thing is energy requirement, because drying is an huge or intensive energy requirement is needed in drying process, right. Because for example, the very basic drying method, if you think about, that is the hot air drying or convective air drying, there the drying bulk air is coming, that need to be heated, and not all the heat that we are putting into the air for increasing its temperature cannot be utilized. There always will be losses, okay. Because of that, sometimes we try to recirculate the exit air, so that some efficiency of that can be utilized. So, drying is wasteful of energy is there. So, it cannot be stated as very high efficient method unless we do some modification in the basic drying mechanism or add some modification to it, okay. So, these are the main things. So, whenever we perform any drying method, we need to follow, we need to see what are the kinetics of drying, how it is proceeding, what is the quality aspect of drying, how we can control or maintain the quality, and also we need to see the energy requirement. That means, to dry unit mass of a product, what is the energy we are putting into the system. Coming to the mechanism of drying, so there are many mechanism prevails, because not all the products that we are dealing that we are taking for the drying, even in the food products, they are not of same texture or structure, okay. If we deal with the solid or paste kind of material, in that the drying phenomena happens because of the liquid diffusion, okay. So, in that case, if the wet solid or the slurry or paste is at a temperature below the boiling point of the liquid. So, in that case the liquid diffusion takes place, and by that liquid diffusion the slurry material will be dried. Now, vapor diffusion, if the liquid vaporizes within the material, that means the temperature is such that the temperature and the pressure level is such that the liquid vaporizes within the material, then the vapor diffusion can take place inside the product as well, and it eventually comes to the surface, and then it is mixed to the ambient. Knudsen diffusion, if drying takes place at very low temperature and pressure, for example, freeze drying. Okay. So, in freeze drying what happened that first we freeze the moisture, all the moisture has been converted to ice first, and then at very low pressure and temperature that is directly sublimed. So, in that case if we dry the material, okay, so the diffusion is neither the there can't be vapor diffusion or liquid diffusion. So, that diffusion is the Knudsen diffusion. Another is the hydrostatic pressure difference, when internal vaporization rates exceed the rate of vapor transport through the solid to the surrounding. Okay. So, internal vaporization rate, that means the vaporization when the surface is coming in contact with the heated air or hot ambience, then the surface is getting dried because the moisture is continuously coming out of the surface. Now, if it happens that from the bulk heating is also possible, so the internal vaporization rate is exceeding the vaporization rate at the outer surface. In that case the hydrostatic pressure difference may generate, and that can cause the drying. Okay. So, basically then from this means we can see that drying can be broadly categorized into convective and conductive drying method. So, convective drying method is that mostly when we dry the product by the hot air, moist dry hot air we use, so that the moisture of the food can be taken away by the hot and dry air. So, there is a convective drying method. Another is the convective drying method, or it is also called the boiling drying method. So, in that case what happened that the liquid is itself boiled, and the pressure and temperature of the chamber is such that the liquid will boil, and eventually it will be coming out of the food matrix. Okay. So, this kind of system we can see in case of the vacuum drying or drum drying kind of mechanism. So, their liquid directly boils up because of the excessive heat, and then it will come out from the material, and it is taken away by the prevailing ambience. In the vacuum also we can't maintain the complete vacuum, we lower the vacuum lower the pressure level compared to the atmospheric pressure. For example, generally atmospheric pressure is 101.32 kilopascal, and when we perform the vacuum drying we keep it from 6 to 25 kilopascal inside the vacuum chamber. Okay. Now, the very important topic, that is the psychrometry. Okay. So, as I said, the if we categorize broadly the drying mechanism, convective drying is the very important and very widely used method. So, for convective drying we used the air which is having moisture content, but it is not fully saturated. Okay. So, it is generally we try to get the dry and hot air, so that that air have the capacity to draw moisture from the food product when they come in contact with the food, right. So, however, the air we are dealing with, the air is not completely moisture free. Okay. So, that air, the ambience air that we are utilizing for drying mechanism. Okay. So, to understand the property of the air plus the water vapor which is already in it, the science of psychrometry is developed. So, psychrometry is basically deals with the study of thermodynamic properties of the moist air, that means the air plus the water vapor present in it. Okay. So, we will see that there are certain laws that we should know that prior, so that we can understand the concept of psychrometry better. One such law is Gibbs-Dalton law. So, what it says that for a mixture of a perfect gases, the total pressure exerted by the mixture is equal to the sum of the partial pressure of the constituent gases. Okay. For example, there is a gas mixture of 3 gases. So, partial pressure of P1, P2 plus P3 will be equal to the total pressure. So, that has been mentioned here. So, applying this equation, what we can say that the total pressure of the atmospheric air will be equal to the pressure of the moisture, that is the water vapor in it, plus the pressure of the air. Okay. So, Pt is the total atmospheric pressure, Pa the pressure of the dry air, and Pv the partial pressure of the water or the H2O vapor present in the dry air. Okay. So, based on this and how this changes, as I said that the thermodynamic properties of moist air, the science of psychrometry has been developed. So, we will try to understand the psychrometry first, that how when a different stream of air is coming in contact with a moist food, how the drying can take place and how the temperature or moisture content or other properties of that air which is coming in contact with the food and then going out of the dryer. So, how that evolves. So, all such thing is important to know for drying analysis. So, psychrometric properties. This psychrometry is an very interesting phenomena, and it gives us many property of that dry air plus moisture present in it. So, this combination, this moist air property we can analyze by psychrometric chart, and there are many property we can find. One such is dry bulb temperature, another is wet bulb temperature, dew point temperature, humidity, relative humidity, degree of saturation, humid heat, and finally humid volume. So, we will discuss them one by one detail. Normally the dry bulb temperature is the temperature which we can directly measure by a normal thermometer. Wet bulb temperature, that is when we keep the bulb of the thermometer wet completely and the equilibrium is attained by that. We then measure the temperature. So, it is always lower than the dry bulb temperature for a particular case or a condition of the air. Dew point temperature is specifically when the air becomes saturated with the moisture present in it. Okay. So, at that temperature this condition happens is basically the dew point temperature. Humidity, we know the amount of moisture present per unit of dry air, that is the humidity. Relative humidity, that how much amount of moisture is there compared to the saturation stage. Okay. So, that is then degree of saturation, humid heat and humid volume. So, one by one we will come to all these properties. The first one is the dry bulb temperature. In short, we can write it as DBT, temperature of the moist air as measured by a standard thermometer. Dew point temperature, the temperature of the moist air at which water vapor in the moist air starts condensing. That means, suppose we have now measured a dry bulb temperature of the air as 38 degree Celsius, and the moisture content is measured, some amount of value of H, okay, humidity. Now, if with the same humidity this air needs to be saturated, then what we need to do? We need to lower the temperature of the ambient. Okay. Now, if we consider this room, if we want to attain the dew point temperature, we need to lower the temperature of the air, and when it lowers in at such an value, so that the moisture present in it, it first make the air saturated, and if further we cool it, they will try to condense out of the air. Okay. So, that temperature is called the dew point temperature, where this condensing start. That means, the air becomes fully saturated, we are not allowing to enter any moisture from the outside, the air is being saturated by the moisture present in itself. Okay. Specific humidity, that is kg of water present per meter cube of dry air. So, when we call specific humidity, specific word actually signifies when we want to mention that how much amount of water present in 1 meter cube of the dry air. Then humidity ratio or absolute humidity, it is defined as the mass of water vapor per unit mass of dry air, mass of water vapor per unit mass of dry air. So, when we talk about specific humidity, we are not considering we are considering the volume kg of water per meter cube of dry air. When we consider the humidity ratio or simply absolute humidity, we are considering mass by mass basis. Now, from the ideal gas law, we know that PV equal to nRT, okay, or this nRT can also be written as m by m, where capital M is the molecular weight of that and m is the mass of the water we have taken. So, applying gas law for the dry air and water vapor, mW, that is molecular weight of water, that is 18.015 into PV by RT, and MA, that is equal to 28.966 PA by RT. Now, how we are getting here PV, if we can write this for vapor, okay. So, MW that is equal to M, that is 18.05 is the molecular weight capital M of water into PV by RT. Here this will be okay. And here for air also this will be MA, that is 28.966 into pressure of air into V into RT. Now, when we talk about humidity, so humidity will be equal to ratio of these two. So, we can get this divided by this. So, ultimately we are getting that because here PV by PA, partial pressure of vapor by partial pressure of air, all other things are constant because they are in the same condition R, T and V. So, H will be equal to 0.622, okay, 18.05 by 28.966 into PV. So, better we can write here okay, better we can write here this way, because if we consider unit volume, okay, if we consider the unit volume, then we can directly write this way, that H is equal to 0.622 into PV by PA, RT will be getting cancelled. So, this will be the expression. Now, relative humidity is what? Relative humidity is the ratio, this is the ratio of mole fraction of water vapor in a given moist air sample to the mole fraction in an air sample saturated at the same temperature and pressure. That means, if in now suppose PV amount of partial mole fraction of the water vapor in a given moist air sample to the mole fraction in an air sample saturated at the same temperature. Okay. So, if the partial pressure we know that now which is maybe lesser than the saturation, and divided by what is the saturation pressure, that we can make that ratio. So, that will become the relative humidity. So, when relative humidity is 100%, then dry bulb temperature is equal to dew point temperature is equal to wet bulb temperature. Okay. So, phi that is equal to, that is the relative humidity, that is XW by XWS, that I says that mole fraction of water by mole fraction in the saturation condition. Now, mole fraction is again we can calculate by PV divided by total pressure, and here PS saturation pressure of the water vapor by total pressure, as we got from this equation. So, PV by PS we are getting for the relative humidity. Now, degree of saturation or percentage humidity. So, percentage humidity is H by HS. HS is the saturation humidity and H is the humidity at any condition of the temperature and water vapor combination. So, this is the degree of saturation or percentage humidity. Next is the humid volume, that is volume of 1 kg of dry air plus water vapor in it. So, the volume of 1 kg of dry air plus the water vapor is humid volume, and its value will be VH, that is equal to 0.00283 plus 0.0045 H. H is the humidity at that condition. Suppose we are talking about temperature of 35 degree Celsius temperature and the humidity is H1. So, here we will put H1 to find the humid volume, and here instead of T we will put the 35 degree, right. So, this is how we can calculate the humid volume of the air, 1 kg air at 35 degree and H1 humidity. Humid heat, that is heat required to raise the temperature of 1 kg of dry air plus its accompanying water vapor by 1 degree, because we know that the heat required to increase 1 degree temperature of moisture is different from 1 degree temperature requirement of dry air, right. So, both the case we need to give different amount of heat. So, that is why we separately calculate both and then add. So, the humid heat CPM, or somewhere you may find it as CS as well. So, this is equal to in kilojoule per kg Kelvin, that is equal to 1.005 plus 1.88 H. So, this is for 1 degree Celsius. Now, if the condition is such that you need to increase the temperature by some degree, so you should include that in your equation T1 minus T2, whatever the temperature difference you need to calculate. So, enthalpy, that is heat content of moist air, that is the sensible heat of dry air plus H2O plus the latent heat of H2O. Okay. So, heat content of moist air. So, sensible heat, of course, whenever the sensible heat increases or decreases, so then that part we need to take, that is MCP delta T. Okay. Here in case of moisture plus dry air, instead of Cp we will use Cpm. So, that part will be there, plus latent heat. So, whatever moisture is there, that needs to be in the vaporized condition. So, at that temperature what will be the latent heat of vaporization, that should be multiplied with the moisture content. Okay. So, sensible heat Cp into T, if we take mass as 1. So, Cp into T plus H into Cpw, that is humidity in there at 1 kg of air. Okay. Cpw into T plus H into lambda W. So, latent heat of vaporization into humidity. So, that is 1.005 plus 1.88 H into T minus 0, here we are taking reference temperature as 0, plus 2501 H. Okay. Now, adiabatic saturation temperature. So, temperature at which air is brought to saturated condition adiabatically by evaporating the water into the flowing air. So, air is becoming saturated adiabatically. So, adiabatically means there is no change in the sensible temperature we can make, but by evaporating the water into the flowing stream. So, we will eventually come into the psychrometric chart reading, and that time it will be more clear to you that how we can find the adiabatic saturation temperature. So, it is kind of, if you can think physically of a phenomena like there is a closed chamber where liquid is sprayed, and that liquid, that makeup liquid is again channelized there, and here is a air stream is entering, which is not saturated initially. Let us temperature is T1 and the humidity is H1. So, when this will go out of this chamber, it will become saturated Ts and humidity will become Hs, because it has absorbed all the all the moisture from it. Okay. So, then it has become, the air has become adiabatically saturated. So, there is no change of temperature has happened, but because the moisture has been added to this. So, because of that this change happened, because of the latent heat exchange. Okay. So, here the same phenomena has been considered, where the moist air with a temperature T1, moisture content W1, and at a pressure P it is entering, and here a thermometer bulb has been dipped into the water which is at T2, and the whole chamber is being insulated properly. This moist air is moving over the water which is kept inside the chamber, and moist air leaving out with a temperature T2, moisture content P2 at the same pressure. So, what will happen if you do the enthalpy balance? Cs, that is the humid heat of this air plus water vapor mixture, into temperature difference T1 minus T2 plus H1, that is initially what was the moisture content, H1 into lambda 2, that will be equal to, finally when it has the humidity H2. So, this will be equal to H2 into lambda 2. Okay. So, this one was there, and what is the moisture has been added to that, and finally what is the moisture content of the final stream in the evaporated state. So, if we solve this, we are getting T2, that is temperature of this water, that is equal to T1 minus lambda 2 H2 minus H1 by 1.005 plus 1.88 into W1. Okay. So, this is how we can calculate the adiabatic saturation temperature T2. Okay. So, all these are known to us, then we can calculate the temperature. So, since T2 will be T1 minus a value, so obviously it will be lower than the inlet temperature. Now, wet bulb temperature, temperature measured by thermometer whose bulb is covered with the wet cloth. Okay. So, again when we covered it by wet cloth, so it will continuously evaporate, okay, and will take the latent heat from this bulb only. So, when this bulb the closed bulb is coming in equilibrium with the surrounding, that temperature we can note down as the wet bulb temperature. So, that will be definitely lower than the dry bulb temperature. So, if you look into the equation that we are getting H minus HW, okay, divided by T minus TW, that is equal to H by MB Ky by lambda W. Okay. So, this we can calculate that how that what is the heat requirement, what is the amount of heat needed to evaporate this moisture content from the wet bulb, okay, from the moist bulb. So, lambda W is the latent heat of evaporation, and H1 and HW, these are the humidity ratio. H by MBKY, this is called the psychometric ratio, H by MBKY, where H is the convective heat transfer coefficient and MB, which is the molecular weight of air, Ky is the mass transfer coefficient, T and TW is the dry bulb and wet bulb temperature of air. Okay. So, here what we can calculate that the heat requirement, that is T minus TW into H, will be equal to lambda W by MBKY into H minus HW. Okay. And if we look into the psychrometric chart, in the x axis we are getting the dry bulb temperature, in the y axis we are getting the humidity ratio, which is expressed in kg of H2O per kg dry air, and along this yellow line we are getting the constant enthalpy lines, and the orange line we are getting the line of the constant wet bulb temperature. Okay. So, we will stop here, we will continue in the next class. Thank you.